advances. And the things in the bottom row in foundational AI are benefiting from insights in physics. And we're bringing together these communities under this one umbrella of iFi to advance both of these fields simultaneously. Some types of things that you're going to be hearing out in the future from iFi are bringing together other types of fields. For example, in particle physics, we study neutrinos, and one of the exciting technologies that we're using to understand the interactions with the neutrinos with matter are called liquid argon time projection chambers. And the data structures from that type of experiment are extremely rich. And we're pairing up that type of data set with people thinking about the embedding of symmetries into neural network structures. And we're hoping that we have more efficient ways of processing particle physics data by taking advantage of those symmetry structures. And then two things that seem completely unrelated: discovering gravitational waves with the LIGO Observatory, one of the flagship NSF operations, and combining that with robots moving around. Well, it turns out that these are similar systems in the sense that you can use reinforcement learning techniques to allow an agent to explore in an environment and figure out better ways of optimizing the operations of gravitational wave observatories. And so in these collisions, we bring together deep physics principles, very rich data sets, exciting discovery opportunities, and it's really a pleasure to be part of this interdisciplinary venture. These ventures are driven to a large part by our junior investigators, and so we want to empower the next generation of researchers. So we have a prize postdoctoral fellowship program where right now we have currently 7 fellows working on various aspects of physics and AI. And then you're going to be hearing hopefully soon about 3 new fellows who are joining our cohort. We are doing education and training, not just within our own community, but further afield. This is a picture of folks at our iFi summer school this past summer. We're going to have another one coming up this coming summer. And I think these people are raising their hand for how excited they are about the intersection of physics and AI. And, it is this enthusiasm of our junior investigators that inspires us to cultivate an inclusive interdisciplinary research environment. And I'm happy in Q&A to talk about some of the things that we're doing on the DEI front, in particular with our early career and equity committee. So this is a super fast, super lightning review of iFi, but just to tell you that we're a unique interdisciplinary institute trying to incorporate physics intelligence into artificial intelligence. And if you think about iFi as being like the quarks inside of a proton, we have physics theory, physics experiment, AI foundations coming together, and we think that our junior investigators are really the glue to create some of the great science that you're going to be hearing about from my colleagues in the future. So now I want to turn to my own research program and tell you how I got where I am. And to do that, I need to tell you a little bit about a puzzle that we were facing back in 2017. So to do this, I need to give you a bit of a particle physics 101. So I don't expect that any of you know anything about particle physics. I'll try to explain some of the issues in the field and give you some hints about where AI might show up, but really try to emphasize that the puzzle was not, oh, should we use AI or not to analyze our data sets, but rather, can we really trust what AI is doing, or are there fundamental concerns about using AI in this particle physics context? So that's what I want to try to explain to you. And again, try to explain my thinking back in 2017 and then see its resolution 6 years later. So the standard model of particle physics, we often draw it in terms of this pie chart that shows the ingredients of the standard model. So these are the fundamental constituents of nature. In orange are so-called quarks. In green are the leptons of the standard model. In blue are the force carriers of the standard model. And the Higgs boson, discovered in 2012, is at the center of the standard model and it endows fundamental particles with their mass. And I think if you look at this picture, you might say, oh, it must be that you make these objects, you're able to study them in a laboratory and study their properties by holding them somehow in your hand. But that's kind of a misleading picture. Most of these particles that you see in the standard model, their properties can only be inferred from the signatures that they leave in particle detectors. So while it's true that the photons, the electrons, and the muons, that these are fundamental particles that we can see in terms of their elementary structure in detectors, the rest of the standard model has to be inferred by other objects. And in particular, the focus of my research is on quarks and gluons. And quarks and gluons, you can't see them directly because they get confined by the strong force. The strong nuclear force tells you that quarks and gluons are not seen in isolation. Rather, they're bound together into composite states with funny names like pion and kaon, or the more familiar protons and neutrons. So these are composite states that have rich internal dynamics in terms of quarks and gluons. Furthermore, not only do you not see these objects, not only do you have to do inference problems to try to infer from the measurements of these particles what the underlying standard model ingredients were, but the types of detectors that we use are heterogeneous with tracking, calorimetry, dedicated muon systems. And we have these collisions happening every 25 nanoseconds. And there's actually researchers in IFI working on trying to do fast machine learning to try to deal with this data deluge. And you have to synthesize information from these different detector systems to infer the particles. And then if you want to infer the existence of quarks and gluons, you have to bundle these particles into these collimated sprays of particles called jets. And trying to understand these jets is a big theme in my own research. And machine learning has played a very important role, both in the reconstruction of individual objects, but also the identification of what type of jets are being formed in collisions. So normally at this part of the talk, I would try to do a movie, but Zoom wasn't behaving yesterday. So I'm not going to do the movie, but rather I'm just going to show you lots of beautiful pictures of jets. Each of these sprays of particles corresponds to, at its fundamental, an elementary particle that was produced in high energy collisions. But because of the confinement of the strong force, you don't see those directly. You can only infer their properties. And jets are a manifestation of the underlying quarks and gluons, but they aren't quarks and gluons themselves. And this mismatch is related to things that we face in artificial intelligence, that we have some underlying concept that we're trying to make decisions about, but the manifestation of that concept might be hidden in some way, either through noise or from some other obfuscation. Here, there's a fundamental obfuscation, that is, the strong force really makes it so that you can't gain information about the underlying degrees of freedom. So I'm going to come back to this quark-gluon thing in a moment, but I did want to just give a parenthetical here, and also gives me an excuse to talk about other IFI-related research. Now, you can ask, why was I such a curmudgeon back in 2017? I've been talking about inference problems. AI is very good at inference problems. Why was I such a curmudgeon in saying, I don't want to do this? Now, part of it was because I was feeling threatened, because I was already developing my own techniques through, as I said, this deep thinking to figure out how to process these jets. And in particular, the heaviest quark is called the top quark, and it has this characteristic decay pattern that gives rise to 3 subjets inside of a bigger jet. And in 2010, 2011, 2012, I was developing an algorithm with Ken Van Tilburg, who is currently a faculty member at NYU. He was an undergraduate at MIT at the time, where we developed an observable called n-subjettiness that basically said, hey, if you have a jet, to what degree is it characterized by 3 subjets? And we were very proud of this, human-derived feature, and we were skeptical that machine learning could beat it. Now, n-subjettiness is the punching bag of the machine learning literature. So every time someone comes out with a new top tagger, they use this as a benchmark to say how many orders of magnitude better they are than our previous method. But again, I was feeling threatened. What changed my mind in part was talking to data scientists, in particular talking to my colleague, Justin Solomon, who does computational geometry at MIT, and realizing that this problem of n-subjettiness actually has a much nicer framing, much nicer than the way that physicists were talking about it. And it's a type of optimal transport problem where you can actually create an abstract space with points and manifolds in an abstract space. And that formula that I had before is simplified when you write this in the language of optimal transport. And for people who know, this is in the language of the Earth mover's distance. And then when this then comes into IFI and collaborating with computer scientists at Harvard and at Tufts, in particular, Demba Ba, who's at Harvard, and Abi Tassisa, who's at Tufts, as well as graduate students Akshana Dogra and Rikab Gambhir, we realized that solving this optimal transport problem is made very efficient using deep learning. And moreover, we can improve the way that we model these jets by using deep manifold learning techniques. So this original 3-subjettiness, you can turn it into a deep learning problem. So here, the an animation is going to show you these purple X's moving around and trying to find the location of the kind of central subject cores inside of this jet. That's what we could do using 2010 technology. But now, once we have this framing in terms of deep manifold learning, we now have the computational power to do much more sophisticated modeling of these jet substructures. And for example, in animation that Rikab, my graduate student, just sent me this morning, here is taking that same event, but now modeling it not as points, but actually as ellipses. And also you can see in the background, hopefully this shows up, there's kind of this purple fog in the background. And what's going on here is that this is actually an event, a jet that had contamination in it. And the machine is learning not only where the central jet cores are, but actually a noise thing that you can filter out. And so it's both learning the noise that's affecting your inference, as well as more exciting, interpretable geometric structures to characterize what's going on. And again, this is enabled by having particle physicists now talk to the data science and computer science communities. And part of my becoming a evangelist is to see, wait, this is something that's actually giving me better ability to process the data that I see in my field, and also ways that are relatively computationally efficient. And again, that's how I turned into an AI evangelist, or part of that. But going back to 2017 and this issue of jets and quark jets and gluon jets, my complaint at that time was, well, what are we even talking about? What is a quark jet? What is a gluon jet? What are these categories that we think we can study at colliders? What do we mean by this? And I need to, again, give you a little bit of a particle physics 101 to explain to you the difference between quarks and gluons as far as a theoretical physicist is concerned. So quarks and gluons come from, let's say collisions at the LHC. We slam together protons at the LHC. At short distances, you make these quarks and gluons. And these quarks and gluons themselves have different properties, and those different properties imprint themselves on the properties of the spray of particle jets that you get coming out from them. And in particular, something that we've known for a long time, since I guess the 70s, is the so-called ultra-Rayleigh-Parisi splitting kernel. This is a core prediction of QCD, quantum chromodynamics, the theory that describes the interactions of quarks and gluons. And via this theory, the prediction is that when you make a quark or gluon that's highly energetic, there's a chance that that quark or gluon radiates additional gluons. This is the same way that if someone gives you an electron and you wiggle it around, that electron will radiate photons. In the same way, if you get a quark or a gluon and you wiggle it around, it will give you more gluons. And quarks and gluons are distinguished by how much charge they have. Quarks have a charge of 4/3, gluons have a charge of 3. So roughly speaking, gluons have twice as much charge as quarks do. And this ultra-Rayleigh-Parisi splitting kernel tells you that, okay, if I'm going to do this radiation, if I'm going to have additional particle production, it's proportional to the strength of the interaction. This is known as the coupling alpha S. It's proportional to this color factor. And it's proportional to two things that tell me about the kinematics of where this extra radiated object will go. Theta tells me the angle at which that radiation comes out. Z tells me the fraction of energy that it carries. And so the fact that these probability kernels go like 1 over theta and 1 over z tells you that most of the time radiation is at small angles. That is, the radiation is coming out collimated. That's why jets form. And that the radiation comes out with small amounts of energy. This is so-called soft limit of QCD, soft meaning low energy. This is what distinguishes a quark and gluon. This is what I would want to see coming out of some type of calculation. Sadly, the strong force confines. And the things that I see are now colorless. So that information that I had about the amount of radiation is veiled behind this confinement screen, if you'd like. And while, yeah, there's an imprint left over, it's fundamentally inaccessible. That color information is fundamentally inaccessible. Plus, it hits your detector, which causes all sorts of complications. And then when it comes around to doing a theory calculation, at least traditional calculations are blind to direct quark and gluon information. That is, you can only infer their presence from calculations and not see it directly. And so if you're thinking about studying quarks and gluons from a machine learning perspective, you ask, how can we identify or classify objects that we can't even define? And this is the complaint that I had back in 2017. And somehow machine learning is going to give me an answer to this complaint. Now, around this time, again, this is 2017, and I'm looking in some of the attendees. So my collaborator, Angelo Koski, is among the participants, and he was one of the people that was, having this rallying cry of like, let's define quarks and gluons in a rigorous way. And different people had different responses to us. One response was, come on, Jesse, don't you know that the quark-gluon problem is fundamentally ill-defined? That is, because of this strong force confinement, you really can't get any information whatsoever. So just throw up your hands and walk away. And while I agree that it's fundamentally ambiguous for the reasons that I said, there's actually multiple possible definitions. And one definition, as you're going to see in a moment, is going to come from machine learning. Another response that we say is, oh, come on, Jesse, don't you know that the quark-gluon problem was solved in the 1990s? Now, people have been thinking about this for decades. What could you possibly add to the story? Okay, first of all, the pioneering work was done in the 1980s, but it is true that neural networks, one of their first applications in particle physics, was trying to tell the difference between these quark and gluon degrees of freedom. And then finally, the one that I love the most is, Jesse, I thought that convolutional neural networks solved the Quark-Gluon problem in 2017. Don't you know about this? What new could you say? And the answer is, actually, yes, I know about this because this was the work of my IFI colleague, Matt Schwartz, who's at Harvard, along with his two master's students, Patrick Kamitsky and Eric Metodiev. And this is actually the origin of IFI was in this. So Patrick and Eric in 2016, they came to MIT as graduate students. And they were very proud of this paper where they used convolutional neural networks to study the spray of particles coming from quark and gluon jets and discriminating between quarks and gluons. And they got spectacular performance in this algorithm. But what I did is I said, I don't care about your machine learning. I let them have it and said, what do you mean by quarks and gluons? And then furthermore, supervised learning is just uncontrolled function interpolation. How are you gaining anything from this type of analysis? And in some level, the answer to this question, that was the PhD work of Patrick and Eric, and convincing me that actually there's a principled way of talking about these categories. And remarkably to me, the more machine learning that we threw at the problem, the more that this problem became better defined. So jets are manifestations of quarks and gluons, but there's no unambiguous way to tell a quark jet from a gluon jet. And yet, we're going to be able to use deep learning to gain a deeper understanding of this, old problem in particle physics. And then you can imagine how you could extrapolate this to other problems, for example, looking for new dynamics that go beyond the standard model. Okay, so in this last part of the talk, I'm going to tell you about this resolution. But for those of you who were connected earlier, I mentioned that ChatGPT thought that I should talk about ethics. And as part of what we do in IFI, we have seminars once a semester that we bring in someone who talks about ethical issues to come talk to our researchers. And we had a really great a talk by Harini Suresh, who was talking about a framework for understanding unintended consequences of machine learning. And, we don't really think about problems in particle physics as having an ethical implications. Certainly this question of quark-gluon discrimination is not one that addresses, other types of discriminatory things that we care about in society. But nevertheless, it was really helpful to hear her perspective and think about some of the biases that show up in societal applications of AI and the ways that those can map onto things that we think about in physics, for example, systematic uncertainties. And mapping some of the issues that she raised to this quark-gluon discrimination problem, it's really at the beginning and the end of this machine learning life cycle where we have to be concerned. So as I said, jets are manifestations of underlying quarks and gluons. But in terms of the original data generation, what this literature refers to as historical bias, what generative framework are we using to acquire our quark and gluon examples? Are we using a synthetic data set that we can trust? Are we using real data? Are there biases in the way that data was acquired? How are we defining these categories in terms of the data that we're collecting? And then once you've applied machine learning to this problem, what inference strategy are we using to make scientific decisions? This is known in this literature as deployment bias. And you have to be very clear about what you're going to be doing with the machine learned model. And so you could have a perfectly trained machine learned model. It gets a really nice value of the loss function, and it could be something that's very powerful. But if you don't use it in the appropriate way, you could draw incorrect scientific decisions. And so, some of the things that we think about in IFI is that, if you're going to leverage machine intelligence, you nevertheless require the making of principled human choices, or at least hopefully principled human choices. And in the example that I'm going to show here, we're going to use real data collected by the CMS experiment at the Large Hadron Collider, a pioneering generation of an open data set that we can analyze. And then we're going to use an inference strategy that's represented by this cute little koala here, and I'll try to explain why a cute little koala is showing up in my slides here. But this corresponds to a particular machine learning strategy for disentangling different categories. Okay, so the key human choice, the domain-specific inductive bias, the thing that we're going to assume, something that as someone who's an expert in QCD would call collinear factorization, is the existence of quarks and gluons as distinguishable categories. And it was kind of funny to talk in this language, right? It's like we're talking about quarks and gluons, we're talking about them as if they exist, but positing it in a statistical sense that they exist as distinguishable categories. This is something that, once we frame it in this language, allows us to tap into machine learning literature. And this phrasing doesn't sound at all like things like natural language processing or a computer vision thing, but remarkably, it does map onto specifically natural language processing. That once you assert the existence of distinguishable categories, you can now tap into, for example, the field of topic modeling, which is used in natural language processing to take corpuses of text and distinguish them into different vocabularies. So for this process, imagine that I have a histogram. You can imagine this red histogram as being a histogram of, let's say, word frequencies coming from a dictionary, let's say a dictionary coming from artificial intelligence. So, you're going to have in this dictionary, you're going to have words in artificial intelligence like loss function and optimization. In blue, you could have the dictionary of terms of physics terms like jets and quarks and gluons. And then if I write a document at the intersection of physics and AI, I'm drawing words from those different vocabularies. And in fact, different people working at this intersection may use more from the red category, the blue category. And so you can have a stack of documents. And then from that stack of documents, could you reconstruct the individual vocabularies of the AI and the physics communities separately? That is, you're saying that the AI community exists as a distinct entity that's distinguishable from the physics community. And when you pluck a researcher like me, then what you're really getting is some interesting combination of those two vocabularies in terms of the words that I'm writing on the page. This statement here is the same as what I said before, that quarks and gluons exist as distinguishable categories. Only instead of these being words in the case of natural language processing, these are properties of jets, like the number of particles inside the jets or the distribution of energy inside those jets. And this link was something that was really surprising to me, more surprising because it then solved the problem. And so in the next two slides, I will solve the problem of what it means to be a quark or a gluon kind of remarkably. So again, the fundamental assumption, the mathematical statement, both of topic modeling and of what happens in fundamental physics, is that when I see a mixed sample of jets, it can be written as a linear combination of quarks and gluons. Now, these are probability densities, so any individual jet that I see, I can't tell the difference from whether it's a quark or a gluon. But statistically, I have properties of quarks, properties of gluons that I'm sampling from, and FQ is the fraction from that population that I'm sampling that has the quarkness of it. So here's a side view of the Atlas detector at the LHC. And you can imagine saying, hey, let's look at all the jets that go into this region, this A region of my detector. That's going to be some mixture of quarks and gluons. Let's look at what's happening in the B region of my detector. That's a mixture of quarks and gluons. And this actually turns out to be a non-trivial assumption. We're making, again, a domain-specific inductive bias to say that makes sense, that when I look at jets in these different regions, it can be written as this linear combination. And that's something that domain experts can argue about whether it's true. But once it's true, then the problem is solved, which when I first learned about this fact of topic modeling really amazed me. This was some work by a group at University of Michigan, and the paper came out in 2016, and we leveraged it in 2017 and 2018, that just given those mixtures, you could then demix to recover the underlying defining categories. And he's like, well, how is that possible? You take random combinations that give you A and random combinations that give you B. How could you possibly disentangle things statistically? And the answer is that probability distributions have a special property. They're always positive. So if I play off A against B, basically try to subtract off B from A, there's a limit to doing that before the probabilities become negative. And when that happens, then you're at a pure category. In this case, let's say quark. So I take A, I subtract off a certain amount of B, determined by this kappa factor, and I push kappa to the max until I hit a place where statistics breaks down, that is, probabilities go to zero. Boom, that gives me my quark category. Do the same in the other direction, that gives me my gluon category. And that's all you need to do. And again, this is a technique that comes from the machine learning community, and it solves my problem about the definition of these categories. We advocated for this in 2018. And by the way, this is non-trivial, and I've had many conversations with my physics friends saying this seems like kind of dark arts. No, it's rigorous statistics. And you can ask about the uncertainties in doing this type of procedure. We advocated this for 2018, in 2018. And in 2019, this is exactly what the Atlas collaboration did at the LHC. They took jets from one part of the detector, jets from another part of the detector, measured the distribution of charged particles within those jets. Again, it's a distribution. Sometimes you get 4 particles, sometimes you get 20 particles. But by playing these histograms off each other, you were able to get the distribution, the ensemble level of, again, things that are proxies for quarks and gluons. Pretty remarkable. Except, wait a second, it seems like I'm still making a human choice. I'm still deciding what properties of the jet that I'm going to study are. In this case, Atlas decided they wanted to study the number of charged particles. Well, why didn't I make a different choice? It still seemed like some type of human bias was coming into this problem. Okay, this seems really cool, but don't these jet topics depend on the choice of jet features that you want to study? And this is the beginning of my realization that sometimes when you face questions like this, you need to go to fundamental physics. And sometimes when you face questions like this, you just need to crank up even more machine learning. And there's certain problems for which the machine gives you a better answer than you might have come up with if you just restricted yourself to domain-specific knowledge. And in this case, this is where this cute koala comes in. If you want to find maximum separability, we can leverage techniques in so-called weak supervision. And in the particle physics community, this is known as classification without labels, or the tortured acronym koala. For people who are in the AI community, this is also known as classification with noisy labels. And the reason why this koala is reading a book is that this koala, which I'm going to show you that technique in a second, combined with topic modeling, gives you a way of really getting the maximum separability between these two categories. Okay, so let me try to explain to you this weak supervision, which again is another kind of miracle that, again, the computer scientist community already knew about, but in the physics community we didn't. And this impeded, in some sense, our adoption of these techniques. And now that we know it, it actually has sped up the adoption of these techniques because we now understand something about the way that machine learning works. So if you open up a machine learning textbook, the first thing you're getting is not weak supervision, but what's known as strong supervision. Strong supervision, otherwise known as fully supervised classification. In this case, we just have two categories, quark or gluon, or more generally, physicists would talk about signal or background. Two categories, binary classification, pure, perfectly labeled examples. If you want to think about this as cats versus dogs, that's fine as well, or just 0 versus 1. This is a problem where we know how to do it. We know that there's many different loss functions that if you optimize them, you're going to get a nice separation between signal and background. And the best you can do for separation in terms of strong supervision, if you have fully perfect labels information, is what's known as the Neyman-Pearson optimal classifier, which says you give me some features X about your object. I'm going to make a decision that's going to be 0 or 1, 0 if I think it's background, 1 if I think it's signal. And basically, if you have enough examples to train this loss adequately, then in regions of phase space where there's 0 signal, that is the probability of getting signal for that example is 0, then you're going to get return 0, it's going to say it's background. In cases where the signal is dominant and there's very little background, then this ratio gives me 1. So you get something that goes between 0 and 1 that gives you some mention of the confidence that you have signal or background. Again, this is the textbook's strong supervision. But in our particle physics case, we have these quarks and gluons. We never see quarks and gluons in isolation. Unless I generate a synthetic data set, I can't actually make individual categories for these. And rather, I'm left with these mixed categories, a mixture of A and mixture of B, a little bit of quark, a little bit of gluon, a little bit of gluon, a little bit of quark. Or if you want to say, like, I go to a park and I see a bunch of dogs and cats, and then I go to a different park and I see a different number of dogs and cats, and I want to distinguish between dogs and cats, but I only have that mixed information. The optimal classifier that tells me the difference between categories A and B, that's all I can do if I try to train this mixed classifier, is different than the classifier that I would use to train the pure categories. And this is one of the complaints that people have about machine learning. They say, well, if you have machine learning and the labels are noisy or you have some kind of contamination, then you're going to get a different answer. But in work that I did with Eric Metodiev and Bengt Nachman, who's a researcher at Lawrence Berkeley National Lab, what we realize is that, and again, this is known in the statistics literature, but we discovered it for ourselves, is that even though these classifiers are different, they make the same decisions. That is, the degree to which you're more background versus more signal, or more quark versus more gluon, is the same whether you have a mixed classifier versus a pure classifier. And so even if you have this contaminated data set, that is, you only have this weak supervision, you only have partial information, nevertheless, you can get the same decision boundaries as you would get with strong supervision. And so combining this topic modeling, which allows us to disentangle jet categories, and this koala, which allows us to find the optimal decision boundaries between categories, you can now have the well-read koala, so koala reading a book, weak supervision meeting topic modeling, where you take a machine learning algorithm, you train it between 0 and 1, trying to distinguish between category A and category B. If we had pure samples, then this distribution would go all the way from 0 to all the way to 1. But it's not. We have a mixture. We have contamination. And the endpoints of the classifier give you exactly the level of mixtures. You can solve for where those endpoints are. And again, you can disentangle these categories. And again, kind of a miracle. Wait a second. This is something coming from the AI community that then allows me to do something that I didn't know how to do using traditional particle physics techniques. So once you use this topic modeling procedure and this koala to extract the quark-gluon fractions using the thing that I showed you in the last slide, the rest turns out to be linear algebra. I still have more slides to go, but at some levels, this is the fundamental insight and what started to change my mind. And then what also changed my mind is that it's not just deep learning. It's even more powerful when combined with deep thinking. And this ultra-Parisi splitting function that I showed you before, in the remaining slides that I'm going to show, it's going to show up again and again. And we're able to interpret what the machine is doing via this fundamental formula. We'll actually see the components of this formula show up in our machine learning applications. But in terms of solving this quark-gluon discrimination problem, it's in some sense solved. And now I'm going to race through to the end of the hour, telling you about other things that are going on once you have this information and what you can do to dig deeper into this data set. So I'm now going to go kind of montage style, a bit too fast. So my apologies. Happy to tell you more about this in Q&A, but just kind of go rapid fire from 2017 to today, showing what we can do with deep learning. Then once we're able to leverage these statistical techniques. First thing is access to data. And I'm a strong proponent of open access, and I want to applaud the CMS experiment at the LHC for releasing open data. My collaborators did the first ever analysis using public LHC data published in Physical Review Letters, where we studied the substructure of jets. And because this was back in 2017, we were doing it without machine learning. And we were able to extract this 1/Z soft singularity structure of QCD, which turns out to be independent of the quark-gluon composition, which is why you get this really beautiful structure, because it didn't know about quarks and gluons. Can we now do the opposite using what I told you about before? Yes, we can. In 2017, we developed this koala method, learning the quark-gluon decision boundaries using this weak supervision. In 2018, using jet topics to define the quark-gluon categories via this technical term of mutual irreducibility, basically the maximal separation between categories. Oh, but now we need a machine learning architecture that I can throw at this mixture distribution to actually find what the best separation is. And here we can again appeal to inductive biases and develop a type of learning based on the particles that we see. Machine learning people will call this point clouds, where we came up with a relatively straightforward machine learning architecture for sets of particles with an interpretable latent space. And this picture on the left-hand side is an interior view into how the machine was trying to solve this problem of disentangling these jet categories using this algorithm that's called energy flow networks. That there's a algorithm that was independently developed 1 year earlier called Deep Sets by the Carnegie Mellon Group. And this way of visualizing what the machine has learned turns out that the fact that you have these kind of rings that are getting smaller and smaller and smaller towards the center, that corresponds to this collinear singularity structure of QCD. Whereas you get closer to the center of the jet, you're more information rich. And that's what the machine is taking advantage of. Also in 2019, exposed to this area of optimal transport and the Earth mover's distance, when in particle physics, we call this the energy mover's distance, since I'm moving energies around. I have different sprays of radiation, a red spray of radiation, a blue spray of radiation, and I can use this optimal transport language to talk about a geometric distance between different jet configurations. That allows me to define a collider geometry that I can then triangulate using these pairwise distances. And now I have a whole suite of geometric techniques that I can take advantage of. With these geometric techniques, we can now start to ask questions about the geometry of our particle physics data sets. And one thing that you'd like to know is what's the dimensionality of your data set? And here is a picture of the dimensionality, but you realize that this dimensionality is a function of scale, that as I mentioned, you have this collision that's happening at short distances. But as I go to longer distances, the actual dynamics changes. I'm getting more particles. I'm getting this confinement. And so the dimension goes from 0 when I have a single quark or gluon to 1, 2, 3, 4, 5, and so on and so forth as I go to lower and lower energies. And this is a machine learned version of the scaling behavior of QCD, that I have degrees of freedom that radiate more degrees of freedom, so the dimensionality of my system changes. Then you look at this plot and you say, wait, you made this plot using public data. There's an underlying theory curve in blue, a distorted curve from detector effects in orange. This is the smearing that comes from the fact that you don't have perfect detectors, and smearing takes points and spreads them out to have more dimensions. That's why the dimension goes up when I have detector smearing effects. But wait, we can use even more machine learning, and actually a technique that we just developed with Anders Andresen, who's at Google, with Ben, Patrick, and Eric, to unfold, that is to correct for detector corrections using certain machine learned reweighting factors. This allows you then to correct for the detector effects and actually get better mapping of what's going on in terms of the underlying physics. So we're in 2020, we have all these things coming together, and then we had some distracting developments. Some distracting developments that kept us apart, in particular COVID. Other distracting developments that brought us together with this AI Institute. And of course, it takes a lot of effort to be director of an AI Institute, but I think it's worth it for bringing these communities together. And now we can kind of come to the crescendo of this story, where putting all the pieces together, again, this is a team effort. The actual paper that came out in a journal was from 2022 with Patrick and then Serhii Kriyan, who's an undergraduate who's now a graduate student at Harvard. I mentioned Erica's already. And then we have Radha Masandria, Preksha Nayak, who are now grad students at UC Berkeley and Caltech, respectively. Anders and Ben. Okay, take quark and gluon jets from the strong force, confront it with public collider data, unfolded for detector effects, disentangled with weak supervision on set-based classifiers using topic modeling, triangulated with optimal transport. And now I have an opportunity to say, in a more rigorous way than I knew how to do before, what's the difference between quarks and gluon jets? So what's the answer? Well, first, going back to the very beginning of my talk, let's see what ChatGPT says. Could you tell me the difference between a quark jet and a gluon jet? It spits out an answer that basically corresponds to my thinking in 2017. Quark and gluon jets can be distinguished by their different fragmentation patterns, which depend on the properties of the quarks and gluons that produce them. Kind of unhelpful answer that doesn't really tell you operationally what you want to do to separate these categories. And in the backup slides, I can tell you, other things that ChatGPT said about quark and gluon jets. But here is, for me, kind of an eye-popping plot that we were able to make through the synthesis of tools, where this plot shows separately the dimensionality of quark and gluon jets. And again, I haven't given the machine any information other than that quarks and gluons exist as categories. I've applied algorithms that take that idea seriously in terms of separating out categories. Because this dimensionality is done through optimal transport, and optimal transport is based on pairwise distances, we actually have pairwise notions of dimensionality, a gluon-gluon dimension, a quark-quark dimension, and a quark-gluon dimension. Gluons have more dimension, which makes sense. Gluons radiate more proficiently, therefore they have more degrees of freedom. Quarks have less dimensionality. They have a lower color factor. They don't radiate as much. And then this thing is in between. We can do a first principles QCD calculation to understand what this is. So this is now taking our interpretive framework, the theory interpretive framework, laying it on top of this plot. And indeed, we see that the slope of these curves tells us about the color factors of QCD. And then the thing that I just fell out my chair when it actually worked, again, this is real collider data, not synthetic. And fingers crossed that it works the way that it's supposed to, because we really do believe that quantum chromodynamics is the description of the strong force. We really do believe that quarks and gluons exist. From a data science perspective, is that true? And the answer is yes. That if you take the ratio here between the red and the green curves, the red and the blue curves, you get this factor of 9/4, which is exactly the ratio of 3/4, a fully data-driven extraction. And then there's a cross-check that we can do, taking those 3/3 together to see this ratio of 1 that says that the whole framework is theoretically consistent. And now with this plot, I can now justify my being a curmudgeon back in 2017. In 2017, what Patrick and Eric brought to me was a definition of quarks and gluons based on this long dashed curve here, where the dimensionality has this slope that is like way different, scale dimensionality, way different from the roughly flat prediction that you would get from theory. Using this data-driven method, we get something that's much closer to a flat distribution. And now it's a fascinating theoretical question about, okay, can we actually predict this deviation in the scale as a function of slope? But I was concerned that we were making decisions in particle physics based on labels that aren't really reflecting the underlying dynamics of quarks and gluons. And here we have a data-driven way that now allows me to sleep well at night. And I'm hoping that these type of techniques play more of a role in my field, where we try to take this data much more seriously and using machine learning to be able to do things that I had no idea how to do with traditional means. So indeed, we gain new insights into the strong force by fusing advances in machine learning with this insights from quantum field theory. And this is an example of the collision coming from my own research. So just to summarize, I gave you this lightning tour through iFi, tried to explain that as a community, we're trying to advance physics research and galvanize AI innovation by fusing this deep learning with deep thinking. I told you about this Quark-Gluon puzzle, and just kind of zooming out, Jets from QCD offers an extreme example where fully supervised learning is fundamentally ambiguous. And it's a useful case study to go in cases where we really do think that there's ambiguities in the way that data is collected. And it's really interesting to think about issues in AI ethics through this lens, where it's scientific data. There are different types of societal impacts, but nevertheless, the same type of quandaries come up in terms of decision-making. And then finally, deep learning for deeper understanding, where I feel like collider physics has crossed an important threshold, where AI is yielding insights that go beyond traditional techniques. So if you were interested in the types of things that I'm talking about, you're welcome to join us in the iFi community. And just to advertise something, we're going to be having our colloquium series that you can watch on YouTube starting this spring in February with a talk on Bayesian interpolation with deep linear networks. But again, this is a way of bringing together two different communities. And it's a thrill for me to be able to represent these two communities as part of this distinguished lectureship between MPS and SCIS, and looking forward to questions from the audience about what you've heard about today. Thanks so much.
Thank you very much, Jesse. Michael, please go ahead.
Sorry, I was clapping. I was
clapping.
There's 100 people out there clapping, but you can't hear them. So I was going to stand in for everyone. No, Jesse, that was awesome. Thank you so much.
All right, thank you.
All right, so my understanding is that that I'm responsible for the Q&A. I didn't get a chance to introduce myself. I'm Michael Littman. I'm the division director for Information and Intelligent Systems, which is the division that oversees a lot of the AI Institute work. And we're really excited that Jesse was invited by MPS and wanted to participate in some way in the visit. So is that right? I didn't see anything on the schedule for how long the Q&A is supposed to be. Like, do we fit into before 3 o'clock?
No, I think we can go for the next 10 minutes.
10 minutes. All right, fantastic. Well, we do have a couple of questions. And again, I want to thank you, Jesse, for a really exciting and enlightening talk. Lots of cool stuff in it. So let me read to you some of the questions that we're getting on our live stream Q&A feed. Todd Lean, who is a program director in IIS, asks, if I understand your description correctly or properly, and I don't, so I apologize if I mangle this. The Quark-Gluon jet identification appears to be an inverse problem regularized by QCD, which I guess is quantum chromodynamics. Is that right? How are the constraints imposed by QCD embedded in the deep network? One could use QCD simulations and hope the network learns the dynamics properly. Are there additional ways to ensure the AI predictions do not violate what we know about QCD?
Okay, excellent question. So in some ways, yes, you're right. This is an inverse problem. You're seeing a collection of data. It's been going through this filter of QCD, and you're trying to infer what happened in terms of the underlying quark and gluon degrees of freedom. And if you had a perfectly trustable simulation, perfectly trustable, fully accurate, and inside that simulation, you knew what the label of quarks and gluons were, then indeed you could use that simulation as a way of enforcing a regularization to make the decision about what you're seeing, whether it's coming from quarks or gluons. The problem is that we don't have a trustable simulation. And indeed, the notion of what a quark or a gluon is fundamentally ambiguous at the level of the simulation. And it has to do with the fact of this thing that I mentioned before, this Altarelli-Parisi splitting function. 1 over z, if you try to integrate dz over z near 0, that's infinity. These are the famous infinities that show up in quantum field theory calculations that have to be dealt with in a special way in quantum field theory calculations. And the way they're dealt with in a quantum field theory calculation, I don't know how to map that on to a statistical inference framework. So yes, it would be wonderful if we had simulations that I could use to help me do a kind of regularization. Instead, what we're doing is saying, let me just assume that these categories exist. And you can, again, argue this. You can argue to what extent are they distinguishable categories? And then you can ask to what extent are there deviations from that distinguishability? But then once you do that, you actually don't need to regularize. You push it to this extreme, or rather the regularization that you do would be a statistical regularization of saying, my data set only has a certain amount of statistical power. So this is a case where the inductive bias or the regularization at some levels comes from the assumption that there's only 2 categories and not 3 and not 4 and not 5. So that's the regularization, is limiting myself to the number of categories. That's where the regularization is coming in. And then there's some statistical tips and tricks, which I have in the backup, about how exactly one does this, even if you have statistical uncertainties from the fact that you only have a finite number of examples from this. But again, if we had a perfect simulation where quarks and gluons were perfectly labeled, then we'd be in great shape. But there is no simulation that has that property, or rather the simulations that do have a property of having labels that can't be trusted because they have this singularity in it. That means that their answers can only be trusted to a certain accuracy. And if you really want to push the frontiers of accuracy, you just can't use simulation-based strategies exclusively.
Excellent. Thanks so much. I mean, one of the things, this is probably going to sound naive, but one of the things that struck me from your talk is, so I was actually, okay, I'm a machine learning person, so I believe in machine learning, but I didn't believe in it for physics. Like that seemed like a mistake, because the last time I formally learned physics was in high school, and they told me things like, these are the equations that govern, physics. And so machine learning is much more loose than that. It's much more flexible, and it didn't comport with me, with what I had learned. But what I came to realize through the way that you were describing it in your talk, it's all basically, we're all just doing statistics. And the reason that we're all doing statistics is because we're getting noisy observations of the world. And so you as a physicist are getting noisy observations of the world, and statistics is a way of trying to back infer what might be going on under the hood. And that's what we're doing in machine learning as well. So it does seem like a better match, a better marriage than I would have predicted naively.
Right. And it requires a change of perspective. Someone who said, oh, the laws of physics are known. Or if I shown you, so there's a difference between the slide that I'm showing here. The slide that I'm showing here is saying, whoa, we have a giant inference problem because actually the ingredients that we think are fundamental and the ingredients that we see are very different. That we have a fundamental inverse problem that we have to solve here. That's very different than if I just show you this picture and say, oh, everything's well known. You can write the equation for the standard model on a coffee cup. Everything is known. But even if the equations are known, even if the governing equations are known, the implications for it can be very, very rich. And a lot of the decisions that we're making are not decisions about, like, do we think that these ingredients exist? They're quite decisions about, well, what are the manifestations of those ingredients? And then even more so, if we want to see small deviations from this picture, we better know how accurately can we make the predictions of this framework if we want to find new physics beyond it. And so we are limited in some sense by our inference accuracy to actually going beyond the standard model, because as you said, we're seeing things through this noisy framework, and it's fundamentally noisy. It's noisy at the level of we do not see the fundamental degrees of freedom. You can only infer, and that's why, again, machine learning plays an incredibly important role in our field.
Gotcha. Inherently noisy. Yeah,
inherently noisy. Yes,
that's really deep. So, okay, we're getting some new questions coming in. Glenn Langston asks, what parameters were measured for input to the learning modules?
None. I mean, not really. So it's the thing that I'm learning for the machine learning, the real machine. So there's, for me, and I kind of glossed over this. When people talk about artificial intelligence or machine learning, for me, it's this broad umbrella that envelops computer science, statistics, data science, computation. It's statistics. It's covering a lot of things because it's often difficult to use them in isolation. That is, you can't talk about a computational framework unless you know the data that you're operating on. You can't talk about a machine learning algorithm unless you know what statistical inference you're trying to draw later. So all these things are under the same umbrella for me. So the strict machine learning part is this slide here, where the labels are, did it come from one region of my detector? I'll call that 0. Or did it come from the other region of my detector? I'll call that 1. But those are labels that are given to you by what you see. So if I go back to this cartoon here, like I just say, oh, I see an object in region A, or I see an object in region B. But I hesitate to use the word self-supervision because I think that's not exactly what's going on here. But the label is coming from where that object was seen. And that's all I'm trying to predict. And then I'm trying to predict that from the properties of the object that I'm observing.
And is the assumption that the A and B are well, first of all, consistent within those regions, and second of all, distinct from A? Like if they were being drawn IID, then you'd think, there's not going to be anything interesting to learn from that.
That's exactly right. So this is a totally non-trivial assumption. It assumes that the A and B mixtures have unbiased jet properties, that is, the probabilities of quarks and gluons are the same in those two regions, and that it's IID up until that in region A and region B, the probability of me selecting something from that category is different. Right. But that's the only thing that differs. Yeah. So what I like about this, and I like the way you're asking the question, is that you're pushing me on the assumptions. And when you push me on the assumptions, I then need to ask from my domain knowledge, are these assumptions valid or not? And that's a really nice conversation to have. If we're arguing about the assumptions, then we've won. We're not arguing about the specific machine learning implementation. We're arguing about what are the assumptions that used at the outset. And then the machine learning, assuming that it converges correctly, should give me a valid answer, at least up into those assumptions.
All right. So while you were answering that question, an anonymous attendee wants to rebut you. Says, some data must be input. I'm guessing energy and angular separation between jets.
So sorry, it's not between jets. It's it's all the various features of the particles. So I showed this cartoon. Sorry, maybe I didn't understand the thing before.
Yeah, I think it's helping to clarify.
The X here are the direction and the energy of all the individual particles in the jet. So if I have 1,000 particles, okay, that's extreme. If I have 10 particles, then I'll have 10 4 vectors as the input. That's the thing that is my input. And then the output is 0 or 1. But I'm not. I think I misunderstood what the question was. That's what I'm training. That's what I'm training on. Yeah, I misunderstood the question.
It was fundamentally uncertain what was being asked. So I think that's one interpretation that was really helpful. I actually thought the question was asking about hyperparameters, but I don't. But now that I read it more carefully, I don't think it was asking that. Yeah. I think probably you got it now. All right. So this is a question that came to mind for me as well. Blaine Heffron, a guest, asked, has there been any work on trying to use more than 2 categories for jet classification and seeing how that compares to the work assuming 2 categories? And I assume that the implicit in this question is like, maybe we would learn that there's other things out there that we just hadn't noticed before.
Yeah, absolutely. So, Jesse had this kind of, why not categories for each quark and antiquark and each flavor, and then each helicity as a term that we use in particle physics. And we have done this study on synthetic data sets. And you can see that it actually does find 3 categories. And it's really cool to start seeing you be able to see the growth of categories as you get more statistics coming in. So when you have smaller number of examples, it can only separate into 2. And if you try to add a third, it just recovers one of the existing 2 categories that you have. The exciting case of this, which we've done, is in synthetic data sets where you try to look for some new phenomena that has nothing to do with the standard model. So this is where new physics discovery comes in. So in the context of the standard model, these are all the jet types that we talk about. So we talk about quarks and gluons. These are these 2 lower things. Then we have specialty quarks like charm quarks, bottom quarks, top quarks, Higgs bosons, W and Z bosons. So these are the types of jets that appear in the standard model. Experts know that taus are jets. So this is a multi-category classification problem that, at least in principle, you could apply this technique and disentangle all these categories. But it's exciting to now insert a new category that you haven't seen before and ask whether this can recover that. And so we have a particular type of advanced topic modeling procedure that actually is able to dig out those additional categories. It's only been tested on synthetic data sets. And of course, the goal is to eventually apply it on real data sets and see if in the vast LHC data sets, there's an additional jet category that we haven't seen before.
Awesome. All right. Let's see. Art Kohler says, great talk, Jesse. So that's all.
Thank you.
Art. It seems as though what you learned about applicable machine learning techniques applies broadly to the subject of mixture experiments, applicable to many difficult to detect interactions in particle physics, but also across the physical sciences and engineering. Do you have a sense of how to define the limits, trustability of this idea?
Yeah. One thing you have to do is ask, are the assumptions correct? So let's do this in the case
the method
of...
can't do that, right? You have that has to be somehow external to the process, yeah?
So what the machine... So what did you say? I missed what you said. The machine can't do that?
Yeah, that has to be external to like the method can't do that, can't answer that question, right? You have to pop out of the system to answer that.
Right. You have to, as I said, you have to make principled human choices. Okay. So in fact, you can get yourself into real trouble when you make those choices and they're not respected by your data structure. Well, we saw this in practice. So I very briefly glossed over this slide where I said we need to, correct for detector effects. Because actually with these detectors, if I try to go to the A and B regions, the A and B regions have different sensors. So if I don't correct for those detector things, then what I find is not Quark versus Gluon, I find A versus B. That's the classification that I'm doing. So when you're given a data set and you say, oh, I have these mixtures, you have to ask, am I sure that I'm controlling for the things that might make this demixing not work anymore? And this is a question where you really have to get the domain experts sitting in a room and saying, yeah, like how do you define these categories? And are we sure that we really understand? And are we sure there aren't secret correlations that would get away from this fundamental formula here? Crucially, this F is not a function of the features X. That's crucial here. If F is a function of the features X, then you can't do this. And so a lot of it boils down to the assumptions. And the question that one got before with regularization is, okay, well, what if this is only approximately true? Then you can use regularized methods to say, okay, I know it's only approximately true. I know I'm not going to get the perfect answer, but let me do a regularized solution that tries to force it in this regime, but understands that I'm enforcing an inductive bias that may not be completely correct in that context. But again, that requires a conversation for how you might think about making decisions in this context. And what we're talking about is making scientific decisions. How do you decide whether something exists or doesn't? How do you decide, based on the data, whether to take one action or another? Ultimately, the person making the decision is a human, which is why I like the synthesis between human reasoning and machine reasoning.
Right. It's a collaboration.
It's a collaboration.
All right. So there's lots of fun questions, including, can you please define curmudgeon? But I think we're almost out of time, and maybe I'll ask this one last question.
Yeah.
All right, so I apologize if I mangle the name a little bit. Suleiman Diallo asks, are there unexpected outcomes when using synthetic data only or empirical only versus synthetic plus empirical data? Any recommended practice from your experience?
Oh, yeah. So this is something that's now starting to be explored because, if I go back to my complaint in 2017, and I basically say to Patrick and Eric, and this is the curmudgeon. Curmudgeon is someone who says, get off my lawn. These synthetic data sets that were used in this training, it's not like it has no information. In fact, it's the opposite. It's including our best understanding of the strong nuclear force, given certain computational limitations. That data, when you synthesize that with real data, could be really powerful. And people are talking about this in sometimes it's called domain adaptation, where you try to make small changes to what you're doing. And indeed, we are working on a project, and it's really cool. What you can do is you can say, I have my data, and I trust my data to make certain types of decisions. That's my real data, the data that I'm collecting from my experiment. Then I have other data, which may be difficult for your experiment to collect, but I trust that if it comes from the synthetic data. So now I have real data that I trust for certain things, synthetic data that I trust for other things, and then I want to push them together. And, if I describe that, a machine learning person would again call that domain adaptation. And it turns out that when we've solved that, what it looks like is it looks like statistical mechanics. That is, the Boltzmann distribution comes out in certain cases from doing this mixture, where if what you trust are moments of distribution, if what you're measuring are moments of distributions, that you actually end up getting the Boltzmann distribution coming out when you're actually doing that analysis. And so it's like a physicsy term rearing its head in a context where you were trying to just merge together two different descriptions of the same problem. Why is it Boltzmann? Because Boltzmann is related to information theory. Information theory is related to inference. And so that's why you end up having this virtual dialogue between the physics and statistics communities. But yes, I think the best practice really is to use all the information that one can use and then make decisions about what you trust that information for different applications.
Outstanding. Jesse, thanks so much for sharing this remarkable field with us and for taking the time to just come in and tell us about it. This is it's super exciting. Hopefully people learned an awful lot. I learned an awful lot. And on behalf of the 85 people who are remaining here, I will clap. I don't know. So I've heard that Zoom actually suppresses the clap. Can you hear the clap?
Yeah, I can see the clap, but not hear it. But thanks so much.
I'm actually clapping, and Zoom knows to silence it, which is very unfortunate for people giving talks.
Yeah.
All right.
Great. Thanks so much. And then advertising our Wi-Fi colloquium for more people who want to learn more about this area.
Outstanding. Yeah, and there's various ways you can learn more about what they're doing. They've got a great website. For NSF people, there's going to be an office hour shortly. So please join us for that if you have some time. And again, thanks for being here.
Great. Thanks so much.
Thank you, Jesse. Bye-bye.